Today what we're going to be learning about are independent and dependent events. These are questions that will involve the use of the word and. So what I'd like you to do before we actually start the lesson is to try example 1 on your own. Use what you know about tree diagrams, events, and the word and see if you can figure out how to answer question number 1. When you are finished, so you're going to pause the video, try the question. When you're finished, come back and check your answers. So pause now, please. Okay, welcome back. For the tree diagram, the first task was to flip a coin. So because there's 2 outcomes, there are 2 branches. The second task was to roll a die. So because there were 6 outcomes, there should be 6 branches. And we've talked about this before, because the probabilities are equal in the first set of branches and the probabilities are equal in the second set of branches, you can just count the number of branches in total. So when the question says, what's the probability of flipping a head and rolling a 2? Start off with your let statements. Let H be flipping a head, T be rolling a 2. And because there's 12 branches and one of them is favorable for a head and a 2, then that means your probability is 1 over 12. These events are said to be independent because whether you flip a head or flip a tail, it does not change the probabilities in the second task. We'll be looking at dependent events later on, but if what happens in the first round does not affect the probabilities in the second round, they are called independent events. And since we're using the word and, in order to answer the third question, how can you answer this question without drawing a tree diagram? Well, the probability of flipping a head and rolling a 2, and means multiply, so that would be the probability of flipping a head times the probability of rolling a 2, so that would be 1/2 times 1 over 6, because 1/2 is the probability of flipping a head, 1 over 6 is the probability of rolling a 2, and that would make 1 over 12. So hopefully you got those answers, and now we're going to be ready to move on to the actual lesson. So in example 2, a drawer contains 7 red paper clips and 5 blue paper clips. One paper clip is taken from the drawer and then replaced. Another paper clip is taken from the drawer. The key in this question is the fact that it's been replaced. This is what makes it independent. And I'll go over why in a minute. Okay, so the probability of the first paper clip being red is 7 over 12. The probability of the first paper clip being blue is 5 over 12. So let's go over how you get those numbers. There are 7 red paper clips and 5 blue paper clips. That means the total number of paper clips in the sample space is 12. In that case, the probability of getting a red paper clip is the number of red paper clips divided by the number in the sample space, which is 7 over 12. The probability of getting a blue paper clip is the number of blue paper clips divided by the total number in the sample space, which is 5 over 12. So a lot of people will say that the probability of a red paper clip is 1 over 7 because there's 7 red paper clips. That's incorrect. And they'll say that the probability of a blue paper clip is 1 over 5 because there's 5 blue paper clips. That is incorrect because you're not taking into account that there are 12 paper clips in total. So for the first draw, the probability of a red paper clip is 7 over 12 and a blue paper clip is 5 over 12. Now here's why replacing the paperclip is important. If you put that paperclip back, the probability of the second paperclip being red is also 7 over 12. And it didn't matter whether you drew a red or a blue because you're putting it back. So the probability of the second paperclip being red is always going to be 7 over 12. And the probability of the second paperclip being blue is always going to be 5 over 12. So again, this is independent because it didn't matter what you drew first. The probability of red-blue on the left side is equal to the probability of red-blue on the right side. So that's what makes these independent. So to find out what is the probability of drawing a red and a blue paperclip, we're going to circle the two branches that are favorable. So a red and a blue, there's two branches that are favorable. You could draw a red and then a blue, or you can draw a blue and then a red. Now, some people might say that the probability of drawing a red and a blue would then be, well, there's 4 branches and 2 of them are favorable. So they would say the probability is 2 over 4, which is 1/2, and that would be incorrect. And the reason why is that these are weighted probabilities. So you can only count the number of branches as being your total and your favorable when the probabilities are equal on both sides. So before, when we had heads and tails, those were equal. And in the second round, when we had rolling a 1, 2, 3, 4, 5, 6, those probabilities were equal. But in this case, the probability of drawing a red and a blue is not the same. So these are weighted events, which we talked about in the first lesson. So you cannot just count the branches. What you have to do is use your knowledge of and or. So drawing a red and a blue paperclip means you can draw a red paperclip and a blue paperclip, or you can draw a blue paperclip and a red paperclip. So let's write this out. So R is going to be drawing a red paperclip and B is going to be drawing a blue paperclip. So the probability of drawing a red and a blue is we've got 2 cases. We can first draw a red and then we can draw a blue, or we could draw a blue first and then we can draw a red. So let's fill these in with some numbers. So the probability of drawing a red paperclip was 7 over 12, and the probability of a blue paperclip was 5 over 12. And the other case, or say or, the other case is a blue paperclip first, which is 5 over 12, and a red paperclip, which is 7 over 12. And if you want to make this even shorter, you can see 7 over 12 times 5 over 12, 7 over 12 times 5 over 12. It's the same. So you can really just take the 7 over 12 and multiply it by the 5 over 12 and then multiply it by 2. And either which way, your answer will be 35 over 72. So question 1 and question 2 were examples of independent events, which means the probability of event A does not affect the probability of event B. Now, the symbol for AND is this symbol here, which is the symbol for intersection. So in this question here, where it says use proper symbols, that would mean instead of using the word and, what you would do is you would use the intersection symbol. So that means the probability is the outcome is in both A and B, and because it's the word and, the probability is just probability of A times the probability of B. Now, if you were drawing a tree diagram, if this is A and this is B, then the probability of A and B are these branches here. So that is the probability of A and B. If you were looking at Venn diagrams, and this was A and this was B, then this middle part is what is the probability of A and B. And your formula is just the probability of A times the probability of B. So that's independent. So independent deals with replacement if you are drawing items. Later on, we'll get to some examples where you are not drawing items, but they're still independent. So now what we're going to do is switch to dependent. So a drawer consists of 7 red paper clips and 5 blue paper clips. One paper clip is taken from the drawer and not replaced. Because it is taken from the drawer and not replaced, these make these dependent. Now, the communication is a little bit harder when dealing with dependent events, and you'll see why a little bit later on. So instead of using R for drawing a red and B for drawing a blue, we're going to use F for drawing a red in the first draw, and F with the bar on top is not drawing a red in the first draw. So that's really just red and blue. So at the beginning, once again, the probability of drawing a red is 7 over 12. And the probability of drawing a blue is 5 over 12. So in the first draw, the probability of drawing a red is 7 over 12. And the probability of not drawing a red, which means you're drawing a blue, is 5 over 12. And here's why we need to make a change. S is now going to represent drawing a red in the second draw. Now here's the issue. If we are not replacing the paper clips, now there's only 11 paper clips left for the second draw. So take a look at this. The probability of the second paperclip being red, given that the first paperclip was red, is going to be 6 out of 11. Because you have one less paperclip in total, and if the first one was red, that means there's only 6 left over. The probability that the second paperclip is not red, which means it's blue, given that the first one was red, is equal to 5 over 12. Oops, sorry, 5 over 11. Because we still only have 11 paper clips because we didn't replace the first one. But if the first one was chosen as red, that means we have 5 left for the blue one. Over on the right side, the probability that the second paperclip is red, given that the first paperclip was not red, which means it was blue, is going to be equal to 7 over 11. There's only 11 paperclips remaining, but if the first one was blue, that means there's still 7 reds. The probability that the second paperclip is not red, which means it's blue, given that the first paperclip was not red, which means it was blue, that's equal to, well, there's only 11 paper clips left, but if the first one was blue, that means there's only 4 left that are blue. So that would be 4 over 11. So the probability of getting a red paper clip in the second round depends on what was drawn first, and the probability of getting a blue paperclip in the second round depends on what was drawn first. And this is the reason why you need to use different letters, because you can't just make this R and this R like you did in the first question or in example number 2, because this R probability is 6 over 11 and this R probability is 7 over 11, and they're not the same. So you can't let them be the same letter. So this is really not S. This is S given F, and this is not really S bar. This is S bar given F. This is S given F bar, and this is S bar given F bar. Again, S means the second red, given that the first was red, and this is the second not red, which means blue, given that the first was red. This is the second being red, given that the first was not red, which means blue. And this is the second not red, which means it's blue, given that the first was not red, which means blue. So the communication is a little more challenging on this, but hopefully the numbers make sense here. So to work this out, we're going to let F be the probability that the first draw is red, and S is the probability that the second draw is red. So to find the probability of a red and a blue paperclip, once again, it's the same 2 branches. So the math is going to be the same. First red and second blue, or first blue and second red. So here's how we go. We want the probability of the first being a red and the probability that the second one is a red given that the first one was a red. Or probability that the second one was a blue, which means not red, and the probability that the second one was red given that the first one was not red. So this is really just red and first one red and second one red given that the first one was red, or first one blue and second one red given that the first one was blue. So just keep those in mind. So that is still equal to red and blue, which is now 5/11, or blue 5/12, and red 7/11. Once again, the numerators and the denominators are the same. So the numerators are going to be 35 and 35. The denominators are going to be here 12 times 11, 12 times 11. They're going to be the same. So you can just take one of them and multiply it by 2. You can do this calculation or this calculation. Either which way, you're going to get 35/66. So the math isn't that much different, but the communication is a little bit harder. So the probability of drawing 2 blue paper clips, that means the first one is not red and the second one is not red. So that means it's the probability that the first one is not red and the probability that the second one is not red given that the first one is not red. So that would be 5/12. So basically 2 blues. So the first one blue and the second one blue, which is 4/11. So either which way, that's going to be 20/132. So these are dependent events. Because the probabilities of the left side are different than the probabilities of the right side. So it depends on which route you take. So that makes dependent events. So dependent events means the probability of event A does affect the probability of event B. So the probability of A and B is the probability of event A occurring times the probability of event B occurring given event A occurred. And dependent events would involve non-replacement if you are drawing an item. Now once again, if your example was using a tree diagram, this would be A, and this would be B, and this would be A given A occurred, and this would be B given that A occurred. This would be A given that B occurred, and this would be B given that A occurred. So to figure out the probability of A and B, It's the probability of A times the probability of B given A. It's also the probability of B times the probability of A given B. If your question involved Venn diagrams, if this was A and this was B, in the middle, you would still have the probability of A and B, but you'd have to remember it's now the probability of A times the probability of B given A. What we're going to look at now are some examples where there are independent and dependent, but not necessarily drawing things out of a hat or a bag or anything like that. So here's example 1. A basketball player has a success rate of 75% for shooting her first free throw. If she makes a throw, she gets confident and the probability of her making the next throw is 90%. If she misses a throw, she loses confidence and the probability of her making the next throw is only 60%. What is the probability that she will make one shot and miss one shot? And is this an example of independent and dependent or dependent events? It's important to figure out first which is it. Is it independent or dependent? So you have to look at the question, and you can even start with a rough idea of the tree diagram. So you know there's going to be 2 free throws, and you're either going to make a shot or miss a shot. So your diagram is going to look something like this. And her success rate for the first free throw is 75%. So if she is successful, it's 75%, which means if she is unsuccessful, it's 25%. Now, if you continue reading the question, if she makes a throw, so this was making the throw, she gets confident and the probability of her making the next throw is 90%, which means the probability of missing would be 10%. If she misses a throw, she loses confidence and the probability of her making the next throw is only 60%, which means the probability of her missing is 40%. So visually you can see what happens in the first round does affect what happens in the second round, because the probability of her making the second shot is 90% here and it's only 60% here. So these are dependent events. Now sometimes you can read the question and you can figure out that they're dependent without drawing the tree diagram. You can just tell by reading the question that you've got different probabilities for the second round. So these different probabilities are that 90% and 60%. The 75%, that was the first round. So when you have dependent events, you need to use 2 different variables, one for the first round and one for the second round. So what we're going to do is say let F be making a shot first round. So that means in the first round you can make the first shot or you can not make the first shot. And S is going to represent making the shot the second round. So this would be making the shot the second round, not making the shot the second round. Making the shot the second round, not making the shot the second round. Now, if these letters confuse you, you really could make four let statements. So F is making the shot the first round, um, N is not making the shot the first round, S is making the shot the second round, M is not making the shot the second round. But that involves a lot of letters, and if you're going to possibly be taking any more statistics or probability or any kind of math courses later on in post-secondary, you probably want to get used to these notations rather than using too many letters. So in this example, we want to know the probability that you will make one shot and miss one shot. So that means you could make the first and miss the second. So make the first and miss the second. Or you can miss the first and make the second. So what we have here is the probability of making the first shot and missing the second shot given that she made the first shot, or she can miss the first shot and make the second shot given that she missed the first shot. So that it would be equal to 0.75 times 0.1, so make and miss, or 0.25 times 0.6, which would be miss and make. And that works out to 0.225. And really to get proper communication marks, because this probability of making a second shot is 0.9 and this probability of making a second shot is 0.6, we really need to add to this saying this is the probability of making the second shot given that they made the first shot. This is the probability of making the second shot given that they did not make the first shot. Similarly, this is the probability that they did not make the second shot given that they made the first shot, and this is the probability that they did not make the second shot given that they did not make the first shot. I know it's a communication nightmare, but unfortunately that's the way it is. So in the next example, we have three different events. We have Ming having a 95% chance of getting an A on her math exam, a 75% chance of getting an A on her French exam, and an 87% chance of getting an A on her exercise science exam. Now, they're three separate events, but there's no way of telling exactly whether one depends on the other. So in this case, you're actually being told that they're independent events because you need to know that so that you'd be able to multiply them together when doing AND questions. So let's let N be getting an A in math. F is getting an A in French. And E is getting an A in exercise science. So this question doesn't actually use the word and, but it is implied. What is the probability? Actually, it does use the word and. What is the probability that she gets an A on her math and exercise science exam? But here where it says, but not on her French exam. So that's really saying, and not her French exam. So what we're looking for here is the probability of getting an A in her math exam and an A in her exercise science exam and not getting an A in her French exam. So that's F with the bar on top. So the probability of getting an A in math is 0.95. And the probability of getting an A in exercise science is 0.87. And we don't want an A in French. So if there is a 75% chance of getting an A in French, remember the probability of not getting an A would be 1 minus 0.75. So that's 0.95 times 0.87 times 0.25. And that will work out to approximately 0.207. So the probability is approximately, don't forget to say approximately, 0.207. Now it's very important that you either can tell that they're independent or be told that they're independent, because that's the only way that you know that you can multiply them. The only way that you know that you can multiply is if they're independent events. Sometimes you can tell by reading the question that they're independent, but in this case, getting an A in math or French, you can't tell whether getting an A in math might affect her being able to get an A in French. So in that case, you're told that they're independent. Here's a question. Suppose that a school's football soccer team has a history of winning 50% of the games it plays on rainy days and 60% of the games it plays on fair days. The weather forecast for the next game day calls for an 80% chance of rain. What is the probability that the team will win the game? So illustrate this with a tree diagram. So what we have here is rain and we have winning. And you have to kind of think about which one is going to depend on the other, because when you make your tree diagram, you have to decide what's going to go on top and what's going to go on the bottom. So will whether it rain depend on whether you win, or will whether you win depend on whether it rains? So the way it works is winning depends on raining. And the fact that you've got two different probabilities of winning, that makes this dependent, which means you need your two variables, not just one. So let R represent a rainy day. And W will represent winning a game. So in the first set of branches, it will either rain or it will not rain. And in the second set of branches, you will either win or you will not win. So, in terms of the rain or the not rain, the weather forecast for the next game day calls for an 80% chance of rain. So there's an 80% chance that it will rain, which means there is a 20% chance that it will not rain. Now, if it rains, there's a 50% chance of the team has a winning history of 50% chance of the games it plays on rainy days. So if it rains, they have a 50% chance of winning, which means they have a 50% chance of losing. And then it says they have a 60% chance of winning on the games on fair days. So days that it doesn't rain, they have a 60% chance of winning, which means they have a 40% chance of losing. So in this case, we're looking for the probability that the team will win the game. So that means it will either rain and they will win, or it will not rain and they will win. So those are your two cases. So we're looking at the probability that it rains and the probability that they win given that it rains. So remember, this is winning given that it rains. This is not winning given that it rains. This is winning given that it doesn't rain. This is not winning given that it doesn't rain. So watch that notation in the second set of branches if it's dependent. So that's the first outcome, rain and win given that it rains, or the probability that it rains, that it doesn't rain, and they still win given that it didn't rain. So that works out to 0.8 times 0.5 plus 0.2 times 0.6, and that works out to 0.52. And there was no rounding there. Okay, so what I'm going to get you to do is to try some on your own. So pause the video, try the last few examples on your own, and then come back to the video and check your answers. So pause now, please. Alright, welcome back. So let's check your answers. It says here that 2 cards are drawn from a standard deck without replacement. So anytime it's without replacement, that means you have dependent events. What is the probability they are both spades? Now you did not necessarily have to draw a tree diagram, but if you did, let F be the first card as a spade, that the first card is a spade. Let S be that the second card is a spade. So the first card, there's 13 spades out of 52 cards, so there's a 13 out of 52 chance that the first card is a spade. That means 39 out of 52 cards are not spades. If you are not replacing, that means there are now only 51 cards. And if the first card was a spade, that means now there's only 12 cards left for the second card to be a spade, but still 39 non-spades. If the first card was not a spade, it goes from 39 to now there's only 38 non-spades, but there would still be 13 spades. But all we're looking for is this one branch, which is both cards being a spade. So that's the probability of the first card being a spade and the probability that the second card is a spade given that the first card was a spade. So that one branch is 13 over 52 times 12 over 51, which is 1 over 17 in lowest terms. The next question, if we let D be disliking vegetables, that means we need the first 4 children disliking vegetables. So that's dislike and dislike and dislike and dislike. And the 5th person has to like vegetables. So if there's a 65% chance of disliking vegetables, the probability of not disliking vegetables is 1 minus 0.65, which is a 35% chance that they will not dislike them. So we have dislike and dislike and dislike and dislike and like. So that makes 0.062. In question 6, this is an example of dependent events. And the reason you know is that the question says that if a person uses UPS, there's an 80% chance that they'll use UPS the next time, which means there's a 20% chance they'll use FedEx the next time. But if a person uses FedEx the first time, there's a 45% chance they'll use FedEx the next time, not 20. So the probabilities are different. So that makes this dependent. So we need to use our two variables. Let F be using UPS the first time. So there's a 70% chance right here. The current market share is 70% for UPS. So currently there's a 70% chance that they will use UPS the first time, so a 30% chance that they will not use UPS the first time. If they used UPS the first time, there's an 80% chance they will use UPS the second time. So that's what S is, using UPS the second time. So the probability of using UPS the second time, given that they used it the first time, is 0.8. So that's a 0.2 that they will not use UPS. If they did not use UPS the first time, which means they used FedEx, the probability that they used UPS the second time, given that they used FedEx the first time, is 0.55. So the probability that they did not use UPS is 0.45. Again, the letters can get confusing, but just try to work it out. This is using UPS the first time, so that means using FedEx the first time. This is using UPS the second time, given that they used UPS the first time. So this is using FedEx the second time, given that they used UPS the first time. If they use FedEx the first time, this is using UPS the second time, given that they used FedEx the first time. And this is using FedEx the second time, given that they used FedEx the first time. So the numbers are more important than the letters because the letters are communication, which isn't as many marks as the application, but getting those communication letters is important as well, just not as important as the numbers. And in example 7, we have independent events. So we just have the probability of passing geography and H being the probability of passing history. To pass at least one of them means you're going to pass geography and pass history, or you're going to fail geography and pass history, or you're going to pass geography and fail history. So remember, if the probability of passing geography is 0.85, then the probability of not passing geography is 1 minus 0.85, which is 0.15. If the probability of passing history is 0.8, then the probability of not passing history is 1 minus 0.8, which is 0.2. Drawing a tree diagram is not necessary, but you might like to give a visual. So this is pass geography and pass history, or fail geography and pass history, or pass geography and fail history, which works out to 0.97. The other way you can do this is think of this as the at least one question. And whenever you have at least one, that means what you want to do is you can take the total and subtract the case you don't want. And the case that's unwanted is to fail both. Now with probability, the total is always equal to 1. 100%. So the other way you can do this is 1 minus the case you don't want, which is failing geography and failing history. So that's failing geography and failing history, which works out to the same 0.97. So that ends your excessively long lesson on independent and dependent events. We will be spending a couple of days on this, so if there's anything that you don't understand, please make note of it and ask your teacher in class. Thanks.